Hello everyone. Today we are going to discuss the problem flight routes from CSES Graph problem set. Let's go through the problem. Your task is to find the k shortest flight routes from Srijala to Metsala. A route can visit the same city several times. Note that there can be several routes with the same price and each of them should be considered. Okay. The first input line has three integers n, m and k, the number of cities, the number of flights and a parameter k. The cities are numbered 1 to n. City 1 is Sirjala and city n is Metsala. After this, the input has m lines describing the flights. Each line has three integers a, b and c. A flight begins at city A, ends at B and its price is c. All flights are one-way flights. You may assume that there are at least k distinct routes from Sirjala to Metsala. Okay. So you need to print k integers, the prices of the k cheapest routes shorted according to their prices. So this is what the problem is. And if you just notice to the constraints of the problem, the value of k is not very large. The maximum it can go is up till 10. So yeah, we can think of some brute force solution or something like that. Okay. Let's see how we can actually solve this problem. So before solving, let's first of all understand what the problem is. So I have just copied this input. I have just copied this input that was given in the problem. So what you need to do is starting from 1, you need to reach city 4 and you need to say k cheapest routes that you can take. And it is mentioned in the question that you can assume that there are at least k distinct routes from Sirjala to Metsala according to the statement that is given. Okay. So tell me, what are the routes that you have? From 1, if you want to reach 4, what are the different routes that you can take? From 1 you can go to 2 and then from 2 you can go to 4, right? So if I just write it down, the cost of the routes, then it is 7 if you follow from 1 to 2, 2 to 4. Then from 1 you can go to 3, from 3 you can go to 2 and then from 2 you can go to 4, right? So the cost will be 3 plus 8 plus 6, that is 17. Okay. What's the next one? From 1 you can go to 3 and from 3 you can go to 4. So it is 3 plus 1, that is 4. Next cost is 4. Okay. What's the next one? From 1 you can go to 3 and from 3 you can go to 2 and 4, that is already explored. From 3 you can go to 4, that is already explored. Okay. Now from 1 you can go to 2, from 2 you can go to 3 and from 3 you can go to 4. So it will be 1 plus 2 plus 1, that is again 4. Okay. This is one route. What else? What else route we can take? There is one more option. What you can do is, from 1 you can go to 2, from 2 you can go to 3, from 3 you can go back to 2 and from 2 you can go to 6. This is also a distinct part, right? So the sum will be 8 plus 2 plus 1 plus 6. Okay, I think we already covered this while we had 17, right? Or am I taking anything wrong? 3, 8. No, we haven't covered it. The 17 was from 1 to 3, 3 to 2 and 2 to 4. That was also 17. And even from 1 to 2, 2 to 3, 3 to 2, 2 to 6, that also gives me 17. Cool. So we have one more 17. Okay. Any other thing? Any other path that we can follow? Any other that you guys can notice? Yes, I can see one more path. From 1 you can go to 3. From 3 you can go to 2. From 2 you can go to 3 and from 3 you can go to 4. This is also one of the distinct route, right? So if you sum up this, if you sum up the cost, it's 3 plus 2, 5 plus 1, 6 plus 8, 14. Okay. So you have one more cost, 14. So I think I have covered almost all the path. You can just see if there are any other path as well. So these are the cost I am getting. Now, according to the problem, you need to return the k cheapest routes. So what you will return? You will return 4, 4, 7. This is what your answer is going to be. And this is what the problem is. So I hope the problem is clear to each and every one of you. Now, how we can actually solve this? Now, if you look up to the constraints of the problem, the value of k is given to you lesser than equals to 10. This means the value of k is very less, right? So we can think of something related to This thing will be in our mind. Okay, how we can actually do this. This thing will remain in our mind. Just tell me one thing. If let's suppose I would have told you, don't give me the k cheapest paths, only give me the cheapest path. If I tell you that give me the cheapest path from city 1 to city n, if I tell you this thing, what you would have done? You would have applied a simple Dijkstra, right? You would have applied a simple Dijkstra and you would have got your solution, right? Now, I don't want only one path, only the cheapest path. I don't want this. What I want k cheapest path. So can you guys think of something like how we can actually solve this? What's the first thing that comes to my mind when I see this? I want the k cheapest path. This means from node 1 to node n, whenever I reach node n, I should have the k smallest roots. Okay, I think we are getting something. We want the k cheapest path, right? Okay, I have an idea. What if for every node I find out k cheapest cost from node 1 to this node. If I am able to find out this by some method, my question is solved. Because at the end, what I will do? At the end, for node n, I will return the k cheapest path from this. So basically what my intuition says is, what I am going to do is, we will see it is possible or not, but what my intuition says, that my first intuition was, okay, what if there was no k given? Basically it was told you that find out the cheapest path from 1 to n. I would have applied a simple Dijkstra. What we do in simple Dijkstra? We have a source node. From that source node, we find the shortest distance to every other node. Now we are told we want the k cheapest path. So what I am thinking to do is, from node 1 to every other node, I find a k shortest distances. If I am able to do this, the job is done. Now just let me see if I will be able to do that or not. Let me see that. What I am telling is, for a node, I am going to store the k cheapest cost. K cheapest cost. Okay. Now, if I want to do this, what if in future I followed certain path and came to this node again with some distance t. I followed certain path I followed, and I came to this node with distance t. Should I keep this distance d or not? How would I check? If I am required to keep this distance d or not among the k cheapest cost, I should be able to check, right? So how will I check? Okay, one option is, for every node I maintain the cheapest cost, right? Let's suppose I have k cheapest cost right now, and one more cost came. One more from one more distinct route, one cost, let's suppose d came. Now let me take an example. Let's suppose the k cheapest cost that you had was 1, 4, 3, 2, 9, and the value d that came was 5. So looking at whatever you have right now, don't you think that this 5 should be inserted and this 9 should be removed? I have just taken an example where the value of k is 5. I already have 5 cheapest distances for a particular node, and from a new distinct path, one more distance 5 came. Now looking at whatever the example I have taken, I am pretty much sure that this d 5 should be inserted and this 9 should be removed, right? Now there are multiple options. One option is you maintain a vector of k cheapest distances. You travel over entire this k, and update the distance. Okay. Now just tell me one thing. If this was the case, which distance you would have updated? If this was the case, which distance you would have updated? Definitely, you would have updated 9. That is the maximum distance, because at any point of time, you want the k cheapest distances to be present inside this data structure, whatever you are storing. Now, what I am saying is, instead of maintaining this vector, what if I maintain a multiset? Instead of maintaining this vector, what if I maintain a multiset? Why multiset? Because you can have distinct routes resulting into same cost. For that reason, I am not using set and I am using a multiset. Okay. And if I am using a multiset, so I know that the last element will be the maximum element, right? So I am only required to check the value of incoming distance with the last distance. If the last distance is greater than whatever the incoming distance is, I will remove the last distance and insert the incoming distance. So this is how, for each and every node, if I maintain the k cheapest routes and apply Dijkstra, I will be able to solve the problem. So the only change that I made over here from Dijkstra algorithm is, in Dijkstra we were maintaining only one distance. Over here we will maintain k distances. And since the value of k is not very large, it is lesser than equals to 10, this won't give you DLE. Let's see the code for better understanding. So this is the code. First of all, I am taking inputs of n, m, and k. Then I am taking the values of adjacency list. A, B, and C. A and B are the values of the nodes, and C is the cost of the path from A to B. Converting to zero-based indexing, and in adjacency of A, I am pushing by B, C. It's a one-way path. Then I am constructing a multiset vector, a vector of type multiset, and for every node I will have this multiset. So this will store k smallest distances. And in distance of 0, I am inserting 0. For 0, one of the cheapest distance is 0, right? So in distance of 0, because 0 is the starting node, I am inserting 0. Constructed a priority queue of pair of LL, LL for distance, node, exactly the same as we do in Dijkstra. While not the priority queue is empty, taking the topmost element of priority queue and popping, if the size of the distance vector for this current node, if it has reached k, what does this mean? This means I already have the k shortest distances, right? In that case, if the size is already k, and whatever the distance I am getting over here for this current node, if it is greater than what the maximum of all these k distances are, what I am saying is, for a particular node, I already have k distances, right? I already have k cheapest distances, if this is the case. And in my priority queue for this particular node n, if I get a distance d, I am told to process for this node n the distance d. And if this distance d is greater than even the maximum of all these k values, so I won't process from this node again, right? As we do in Dijkstra, what we do? We calculate one distance. If we get a particular node for which if I am told to process a distance that is actually greater than whatever the minimum value in distance vector is for that particular node. If that is the case, we don't process, right? We simply continue. That's the same thing I am doing over here. If for the current node, the distance vector size has already been reached k, and if the maximum of all those k distances is still lesser than the value d, so I won't process this input. So I will simply continue. Otherwise, for every node weight pair from this adjacency of current list, what is the new distance? New distance is whatever the distance I have plus this age weight. Now for this particular node, if the distance vector size is lesser than k, this means I am still left out with some k cheapest distances. So I can simply push it. So in my distance of node, I simply insert this new distance and I will process this node with this new distance as well. So I insert it inside my priority queue. Otherwise, if the value k is reached, so in that case, I am just checking if the last value is greater than whatever the incoming value is. If that is the case, so I will remove the last value insert the new value and process the node with this new distance. So by doing this, what I am able to achieve at a time in my priority queue for a particular node at a time in the multiset, I don't have access of more than k elements. This was like one of the questions that was asked to me in my Amazon interview as well. So this was only like not the same problem, but there was a problem in which for every node you wanted to maintain some distances and the value of k was given. So over here, by just doing simply these operations and these operations, simply by doing these operations, I am able to achieve that at a particular time inside my multiset for a particular node, the number of values does not exceed k. If you would not have kept this situation, then if you would not have kept this condition, then in that case the values may have exceeded k because there are multiple different routes, right? And you would have got TLE or MLE as well. So I hope this thing is clear to each and every one of you. Once you're done with it, just for the last node, print the k distances that you have. You already have it in sorted order because we are using a multiset. So just print it. So this is how actually you can solve this problem. I hope the solution was clear. Thank you.